All right, I think we have that settled out, so I'll just continue with the presentation. So an outline, I'll be going over the motivation for this work, explaining our methodology, and then talking about applications to flat plate boundary layers, and then a Mach 8 nozzle that we simulate, and then I'll go over our conclusions. So our motivation for this work is that as scale resolving simulations become more and more prominent, the problem of enforcing realistic inflow fluctuations to start turbulence in the simulation remains an issue. There are many methods that have been tried in the literature, and many work to varying degrees for certain cases. In general, you have your high fidelity type inflows like recycling and rescaling, using turbulence libraries, and some more exotic techniques that use machine learning or POD. These work very well. You can get a fully developed turbulent flow with a very short development length, but these usually require some sort of extra simulation or a database. So these don't have as much flexibility as we might like. There are also low-cost types of inflow, which basically enforce synthetic eddies into the start of the domain. These are things like random forcing, digital filtering, or the synthetic eddy method. So these have the advantage that you don't need an extra database in order to generate the fluctuations, but these usually require a longer development length for the boundary layer to become fully turbulent. And then when you get into the problem of spatially developing 3D geometries that might have secondary mean flows and lots of turbulence and anisotropy, it becomes even more challenging to prescribe inflow for those kinds of flows. So our strategy is that we wanted to have a cheaper method for implementing forcing in our scale resolving simulations that does not require an auxiliary simulation. So our strategy was to use synthetic eddies computed from resolvent analysis. Resolvent analysis is a general technique for determining what sorts of modes are amplified by the linearized dynamics of whatever operator that you're working on. So in our case, we're working with a Navier-Stokes operator. So resolvent analysis will tell us what types of modes the linearized Navier-Stokes equations will amplify. So the question is, why did we want to use resolvent modes? That's because there's a lot of literature showing that resolvent analysis can actually predict the coherent structures that you might find in a fully turbulent flow. So we've observed this for jets, pipe flows, channel flows, boundary layers, all these flows where you might need to do a scale resolving simulation with hundreds of thousands of CPU hours in order to compute these SPOD modes to see the structures. You could use resolvent and identify the same structures. So it offers a low order method for computing these coherent structures. So if anyone knows resolvent analysis, then our formulation is pretty familiar to you. We essentially linearize a Navier-Stokes operator, like I was talking about, that gives you your linear operator L, which in our case is just a matrix. We then Fourier transform in time, and if your flow is spatially homogeneous in some directions, you can assume a wave-like disturbance, and that lets you write it in the equation in the box. And that operator with the inverse around it, that is what we call the resolvent operator, and we denote that as H. And in order to get the modes which are most amplified by the flow, you would take the singular value decomposition of that, which is H into U sigma V conjugate transpose. And in regards to turbulent flows, the way that the resolvent operator works is that you essentially have the resolvent operator as H. It takes in some nonlinear forcing term from the Navier-Stokes equations. So it maps that to a response, which is the Q hat vector. That goes back and becomes the nonlinear terms, and that cycle sort of repeats. And that is the cycle for turbulence that McKeon found. So resolvent modes for inflow forcing. There have been previous attempts to use a similar technique. The most, I think the most notable one was by Rout in 2018. He used a genetic algorithm to optimize resolvent modes computed from a pipe flow to fit second-order statistics from DNS, and then he imposed that into a DNS of a pipe flow, and then he found that he got pretty good, decent development length when compared to techniques like digital filtering. A problem with this technique was that it wasn't very general, and that he had to manually select which modes he wanted to pick. So if he went to a different flow, you might have to manually select different modes again. Another person who did resolvent inflow forcing was Solent, 2019. They found a longer development length than similar methods like than the synthetic eddy method, but they had a sort of systematized way for picking which modes to use. So in spectral space, they would plot out the gains of the modes, and they would select modes that had a high gain, which are shown in the red in the contours. So our strategy is to sort of combine both of these ideas. So the genetic algorithm is very nice for getting your modes to match second-order statistics. So you can match Reynolds stress, TKE, the RMS values of the transverse velocity fluctuations, any combination you pick, really. And we essentially have an automatic way for detecting which modes we want to use. This means that we don't have to manually select modes that we want for a different inflow or for a different freestream condition. It's all done automatically. Another way that our method differs is that we include an eddy viscosity model into our resolvent operator. So if you remember that cycle I was talking about the resolvent operator mapping the nonlinear forcing to the state response. If you don't consider eddy viscosity into the operator, you're essentially assuming that the forcing term is neglected. And that can be a good or a bad approximation depending on the flow. But what Simon and Fan found was that for these fully developed boundary layer type flows, when you include an eddy viscosity model, you will drastically improve the agreement between the resolvent modes and modes computed from SPOD. So you can see essentially the effect of the eddy viscosity is to diffuse the modes in the wall normal direction, which again improves agreement drastically with the SPOD modes. In particular, I like the work of Fan because they did this for a hypersonic turbulent boundary layer, which is one of the cases that we will be trying. Okay, so our technique in general is pretty simple. First, we extract mean profile from a RAND solution at whatever forcing plane you desire. In this case, I'm showing the axial velocity and temperature profile at Mach 5 for a nozzle, but these are actually 1D profiles that we're taking. They're not 2D. You can also take out the TKE and the eddy viscosity profiles in order to perform the genetic algorithm and compute the resolvent operator with the eddy viscosity term. Second step that we do is we compute resolvent modes. These are some examples of the modes identified for this pipe flow. You can see that we can sort of pick which modes, where they respond in the boundary layer, either deep inside the inner layer or larger outer scale structures that sit higher up in the boundary layer. We'll go over the specific technique that we go for picking these modes. And then we find a smart way of combining the modes, and then we superimpose them onto the RAND's mean flow to initialize the LES. So those are some examples of the actual time-varying flows that we impose on one of our simulations. You can see that we get some fairly realistic turbulent structures occurring for the axial velocity and temperature. Okay, so like I mentioned, we have an automatic way for selecting which modes that we pick. Essentially, the idea is that you can pick the speed of the mode, since the resolvent operator in our case is a function of the temporal frequency and the spatial wave number. And then using a dispersion relation, you can say that the speed of the mode is given by C. So if you pick C to be, for example, 0.5, that will give you a mode typically responding deep inside in the inner layer of the boundary layer. If you pick C to be like 0.99, you'll get a mode that fluctuates at the edge of the boundary layer. So this allows us to pick the heights that the modes respond at. The second step that we do is that we compute the low rank factor across wave number space. So we take alpha and beta, we compute the resolvent operator for a range of those values, and we see where does the resolvent operator selectively amplify modes. So where is the first singular value of the resolvent operator high? And that's sort of that contour plot you see on the right. You can see that only for certain combinations of streamwise and spanwise wavelength will the resolvent operator give you a low rank sort of response. And when it does that, we basically assume that those are where the turbulent structures live, and that's where we sample. And those white dots are an example of where we would sample those modes, right in that low rank region. Okay, the genetic algorithm. So we're using a very similar method to route, and we show in some of our previous work that we're able to get good agreement between a prescribed second order statistic profile and the resolvent modes. It's not perfect, obviously, but we were optimizing for TKE, Reynolds stress, the wall normal, and the spanwise velocity fluctuation RMS, and we show that we can essentially achieve good agreement between all four of these things, which we did not really know a priori before trying this. So that was a good surprise. Another surprise was that in the case of, for example, a hypersonic turbulent boundary layer, the temperature and density fluctuations can become a large fraction of the mean values. So we did not optimize for the temperature at all, yet we still see that we're achieving a similar sort of magnitude in the temperature RMS compared to a reference solution. So that's good. That means that our modes are physical. They're doing something to get a correct temperature and density field, even though we're not, again, optimizing for that. So here's an example of one of our inflow forcing fields for a Mach 8 boundary layer. On the left is the resolvent forcing case using no eddy viscosity model. And on the right is the resolvent forcing case using an eddy viscosity model. And you can see that the main difference is in those outer layer structures, where when you don't have an eddy viscosity model, there's no real coherent structure to those outer scale boundary layer structures, versus when you include the eddy viscosity model, you can see that you get eddies on the order of the boundary layer height, and it almost looks like a very heavily filtered LES solution if you really squint your eyes. Okay, now onto our simulation methodology. So all the cases that I'll be presenting from now on were computed using NC State's ReactMB code. It is a high-order finite volume code that uses structured multi-block grids. So this allows us to simulate some fairly decent, fairly complicated geometry. The turbulence modeling is implicit, unless I say otherwise. So we have no model for the turbulence. We have no turbulence model, and that's because we're using relatively fine grids. Our LES numerics, we're using a 6-order piecewise parabolic method with a Ducrot switch, and that will shift the velocity and pressure reconstruction to a 6-order central difference scheme away from shocks. So that allows us to get higher order reconstruction. And then we advance in time using Crank-Nicholson with an implicit dual time stepping method. That lets us take relatively big time steps, which is nice. Okay, the next few slides will just be going over a summary of our SciTech 2026 results. There are a few issues with these simulations, mainly that there was a bug in how we were enforcing the resolvent forcing, but I still think that we can still take away some good conclusions from this study. So there's a lot of parameters that you can select for this technique, including like which modes you sample, how you sample them, whether you include the eddy viscosity model. There's a lot of things that we wanted to see if they would affect the resulting boundary layer. So we have 6 cases that use a variety of different variations of the resolvent forcing method. And what we see is that for our first order, second order statistics, they tend to agree fairly well. You'll see that the curves that differ a lot, which are the light blue and the light green curves, those are not using the eddy viscosity response modes, which is what our formulation currently uses. And all the other curves, which sit on top of each other, they use some variation of eddy viscosity response resolvent mode. So you can see that regardless of how many modes you pick, or which specific modes you're sampling, or how your genetic algorithm sort of optimized, you'll still get the same sort of boundary layer developing. So that's good. That means that our technique is relatively insensitive to the specific modes and how you combine them, as long as you're using the right modes. Last slide in SciTech, just showing the streamwise development of the Reynolds stress. So this is a slice in the XY plane of a boundary layer. You can see that it takes a little while for the turbulence to develop around 10 boundary layer heights down, but you can see that for most of the cases, they are transitioning to turbulence in the same spots. And you can see that the cases that don't, that look a little crazy, those are not using the eddy viscosity response modes. So again, you need to use the eddy viscosity response modes, and then it doesn't necessarily matter which ones you pick or how you combine them. As long as you get a good enough answer, you'll get a similar sort of boundary layer development. Okay, so like I said, those simulations weren't amazing because there was a bug in the response in the implementation for the resolvent forcing. So I did some further coarse grid flat plate simulations in order to really verify that our technique is working. These are going to be Mach 8 and Mach 2.5 turbulent flat plates with the same preconditions used as Zhang in 2018, who's one of Leon Duan's students at OSU. Our grids have relatively fine streamwise spacing, but they are significantly coarser in the spanwise direction than you might like for not using an implicit LES model. We use 5 flow-through times to initialize the turbulence, and then we use another 5 flow-through times in order to take statistics. Okay, so the Mach flat plates. What do we see? We see that the U velocity profiles have excellent agreement with the reference DNS. You can see that we're essentially sitting right on top of the DNS for the dimensional velocity and for the Van Dries transform velocity. Temperature, we are over-predicting the DNS by a little bit, but that could be because of our solver or some other settings that we're using. And our Reynolds stress profile, again, is sitting essentially right on top of the DNS, maybe a little bit of a higher response in the inner layer. I'm now going to compare the boundary layer development with the DNS. So you can see the boundary layer heights for delta 99 and the momentum thickness. They have the similar growth rate to the DNS, so that's good. If we compare the skin friction, we can see that around 10 boundary layer heights in, we're already starting to develop that turbulent profile. And if you compare the error between the skin friction over 2 and the rate of change of momentum thickness, which is the von-Karman integral equation, we satisfy that in roughly 30 to 35 boundary layer heights downstream. Now, for reference, the DNS that Zhang did in 2018 with a recycling scaling method needed 50 boundary layer heights in order to satisfy this equation. So we're showing that essentially we're doing, I would say, fairly better than a recycling rescaling technique, which is considered, state of the practice for these sorts of DNS simulations. So the whole point of the resolvent forcing technique was to impose these modes which resemble coherent structures into the boundary layer. So I wanted to see, is it actually doing this? So here we're looking at a wall normal slice of a Mach 8 turbulent boundary layer, and this is the whole domain in the spanwise and streamwise direction. So if we zoom in at the inflow, we can see that the resolvent forcing is putting in these streaky structures that have a similar magnitude and sort of spanwise width as downstream. Obviously, there's some clear periodicity happening here because the resolvent forcing is not perfect. But you can see that we very quickly start to develop these realistic structures that stay relatively the same as you continue downstream. Then if you look further downstream again, you see a sort of similar structure for these inner layer streaks. It's at a y plus height of 15 by. We compare spanwise spectra for the u velocity and the w velocity fluctuations. And these are taken at the colored lines shown onto the boundary layer. We can see that where the resolvent is implemented at the beginning of the simulation, it does not really look like a turbulent boundary layer at all. You can see that there's spikes in the spectra. The shape is completely wrong. Not great. But by the time we get to the blue line, which is about, I would say, 5 boundary layer heights downstream, we're already sort of matching the spectra downstream. So that's showing that these turbulent structures are sort of bursting immediately right after the inflow, and we are basically getting the full spectra that we would expect right away. This is another slice at y plus equals 100 in the log layer. You can see a similar idea. So the resolvent forcing is putting in these larger structures, which now have a wider spanwise width. And you can see that qualitatively, these resemble the structures that develop later on in the boundary layer. And again, you look downstream again, it looks pretty similar throughout. And if we do a similar type of analysis where we can compare the spanwise spectra, we still see that at the inflow, not really a great agreement with the rest of the boundary layer, but pretty soon afterward, the spectra are all collapsing on top of each other, which is what we would want to see. Okay, this is a 2.5 plate. Won't go into as much depth as this, but we can see that the U and temperature profiles agree nicely with the DNS. We are sitting higher than the reference DNS in the Van Dries transform plot, but I'm pretty sure this is to do with the coarseness of our grid in the spanwise direction, since I think that's a response typically you would see when your grid is under-resolved. This is a streamwise development. You can see that von-Karman integral equation is satisfied in roughly 20 boundary layer heights. The data is pretty noisy, but you can still see that. And for reference, Zhang's DNS at these conditions took 20 boundary layer heights with recycling and scaling and 40 boundary layer heights with digital filtering. So I think we're doing a much better job than some other synthetic turbulence forcings. Okay, so this is the next application of our technique, and this is for simulating the freestream tunnel noise in a hypersonic tunnel. So most experimental transition data is obtained from conventional hypersonic tunnels, and these are pretty noisy because the walls of the boundary layer are turbulent, and these will emit acoustic radiation into the test section of the nozzle, and that the frequencies of these fluctuations can overlap with second mode instabilities, and so they certainly have an impact on the transition of the boundary layer from laminar to turbulent. So what most notably Dewan's group at OSU has been doing is using DNS to recreate the full spatio-temporal structure of the tunnel disturbances with DNS. And the computational cost for these grids is increased because not only do they need to resolve the turbulent wall boundary layers, but they also need to make sure the grid is refined in the core flow so as to not excessively damp out the acoustic fluctuations. Oh, forgot to mention that the reason why they're doing this also is to use these DNS simulations as an inflow boundary condition for DNS transition over cones, for example. So we would like to see if we can get a similar sort of flow field structure using large eddy simulation instead of a DNS grid. Okay, this is just some validation of our numerics. Earlier, we were seeing that we were excessively damping the acoustic noise emitted by one of our simulations. That's because we did not use the Ducrot switch for the pressure reconstruction. On the bottom, we ran the simulation using the Ducrot switch. What we see is that we get much finer grain scale acoustic fluctuations, and we sit right on top of the DNS reference spectra, which is good. That means that we're resolving the free stream fluctuations nicely, and our numerics aren't excessively damping our free stream field. Okay, so the LES that we decided to do was on a Mach A nozzle with a similar contour to the Sandia Mach A wind tunnel. This is the Dewan's group has already done a simulation for this exact geometry, so we felt like this would be a good comparison to see the difference between the LES and the DNS solution. We're using a structured multi-block grid, and you can see that we use this nesting to sort of increase the density of the cells in the downstream section of the nozzle where we want to resolve the free stream fluctuations while decreasing the cell density in the throat. That way we're not excessively packing in cells where we don't really need them. We're using an isotropic spacing of 1 millimeter, which is about 13 wall units, give or take. And that gives us a total cell count of 444 million cells. And that's over 71,000 blocks distributed over 4,500 cores. So, LES at the Mach A nozzle. We're using the same conditions again as Dewan did in 2019. And to get our statistics, we evolved the LES for 10 total flow through times. So 5 to get the flow initialized, and then another 5 to take statistics. We're using a time step of 4e-7 seconds. And each of these simulations from start to the end of taking statistics takes about 112,000 CPU hours, which really isn't too bad given the size of this geometry. So in order to make the tunnel wall boundary layers turbulent, we're using a cylindrical formulation of the resolvent operator. So this is similar to what we were doing with the flat plate, except now our resolvent operator is in cylindrical coordinates. So this allows us to extend the same methodology pretty seamlessly to the axisymmetric nozzle. Actually, for this case, we did not use an eddy viscosity model. That's because our turbulence model was giving us a sort of bad response where we wanted to force. So we turned that off for this case. It's not needed if your boundary layer is quite thin and doesn't have those large outer scale structures where the eddy viscosity is really affecting the flow. So, okay, these are some results for our LES. You can see in the top left plot, we're plotting the Mach number of the nozzle. Top half is the RAND solution, and the bottom half is the LES solution. So you can see that we're getting a nice turbulent tunnel wall boundary layer developing. On the bottom left plot, we're plotting contours of the temperature, and you can see where I've zoomed in sort of the forcing plane where we're enforcing the resolvent fluctuations. You can see that pretty downstream, we're already getting these turbulent structures to develop. And then if we compare the mean profiles of our LES with the DNS of Dewan, we can see that we're getting relatively good agreement with what he's getting. So how are we doing with the freestream environment? Well, I'll say qualitatively, it looks like we're reproducing sort of a filtered solution from the DNS. As you can see, our boundary layer has a similar sort of characteristic as Dwan simulation. And we can see that the freestream noise, we certainly don't have those sort of high frequency structures that were present in the DNS simulation. Those have been filtered out by the grid. But overall, I would say qualitatively, the results look pretty good. And yes, these are just some statistics that we've taken in the core flow of our LES simulation. So on the top are plots of the power spectral density of the freestream fluctuations on the left, and on the right is the power spectral density of the wall pressure fluctuations. So we can see that for the freestream, we're agreeing well in both the spectral roll-off and in terms of the magnitude. And then at the wall, we're slightly under-predicting the DNS, but the spectral roll-off, again, is agreeing fairly well. I will note that we do drop off, and we don't resolve the highest frequency content that the DNS is getting. And again, that's because we're using a coarser grid, so we're filtering out that content. But if you actually compute if you use that frequency and compute sort of the speed of the acoustic disturbances, we can find that that point where it's dropping off is at the grid resolution that we're using. So we're pretty confident that this is because of our grid. The bottom left is comparing the power spectral density, pre-multiplied power spectral density of the pressure fluctuations in terms of the spatial directions. So in the span-wise, stream-wise, and in the, well, I guess there's no one-on-one direction, but in the XY directions. So what we can see is that we get good agreement with the DNS in terms of the span-wise spectra, in terms of the stream-wise spectra, which is those blue curves sitting on top of the dashed black line, for most of the wavelength space, except for in the smallest wavelengths. And then for the Y and Z power spectral densities, we can see that we're agreeing well up until those middle frequencies where we're seeing a bunching up of energy occurring, where the DNS did not have that. So these are preliminary results, so we're still investigating why exactly this is happening. My running theory is that we are running an implicit LES, so maybe our numerics are not damping out the fluctuations appropriately, so perhaps the inclusion of a subgrid-scale model might improve the agreement there. And then on the right are contours of the two-point correlations in the streamwise and, I guess, transverse directions for the pressure fluctuations. We can see that the shape of these is sort of like an X pattern, where they have a definite size, a definite sort of shape for those larger scale structures, but as you get smaller, they become more and more isotropic. Cool. So go over conclusions. So we showed that we are able to use resolvent inflow forcing for span-wise periodic flows, like a boundary layer or for an axisymmetric nozzle. And we showed that we actually develop a fully turbulent flow faster than conventional methods, or about on par with things like recycling and rescaling. We applied this method to large eddy simulations of the Sandia Mach 8 tunnel, and we showed that we were able to reproduce the correct grid resolved frequency content, but we do overpredict the energy in the middle wave number content. Future work. Trying to figure out why we're bunching up energy in those middle wavelengths and trying to attenuate that is something that we'll be looking into. Again, maybe the subgrid scale model will do something to help with that. Another avenue of work that we want to look into is adding back in the high frequency content into the LES data. So as you saw, we were cutting off those highest frequencies, and those might impact transition, for example, for second mode disturbances, but we're not entirely sure. That's still an active area that we really want to look into. Perhaps we could just use the LES data that we already have as an inflow boundary condition for a transition DNS. And then in terms of the resolvent forcing, we would like to look at inflows of simple geometries with complex mean flows. So what does that mean? That means like a square duct that has secondary mean flows in the corners. You don't really have a nice way of enforcing fluctuations for that, unless if your flow is simple and it's basically just a straight duct, then you could apply recycling and scaling maybe and do that. But for example, for a rectangular nozzle, there's no real easy way to do recycling and scaling in that geometry. So there might be some avenue to employ resolvent forcing there. And then inflows of complex geometries with complex mean flows. That's in the future. Maybe like a scramjet, where those have very complicated flows. There's no easy way to put in forcing for that. So perhaps a resolvent operator can help us identify structures in that sort of flow. Acknowledgements. There's funding by the ONR. And yeah, thank you.
Resolvent finally quote out.
Yes.
The condition number.
Condition number for?
Yeah, you have this SVD.
Yes.
Truncated.
Yes.
What is the condition number that you're kind of involved?
It's I don't know, maybe like 1E4. Or sorry, 1E4. So it's not really high. We have no problem taking the inverse of it with MATLAB. So it's not really too much of a problem in terms of that.
So when you say in your constraint functions, you have these other profiles that you want to match.
Yes.
You said optimize.
Yes.
What's your norm that you optimize?
I believe it's just the L2 norm, just matching those profiles with the L2 error norm.
Does it matter what norm you optimize?
I'm not sure. I haven't tried it. I found that I get typically okay results with the current genetic algorithm that I'm using, but it might be interesting to see like a different norm, how that might affect the optimization. It's a good question.
I have one other. We have one more. If I want to apply these methodologies on rough surfaces,
yes.
You're matching the DNS, those versus perfect walls, I think.
Yeah.
Are there modifications that you would have to do?
I think that there has been LES done for rough walls. I'm not exactly sure if that same methodology that we use could use that, but resolvent analysis for rough walls is certainly a thing that exists. So there is a potential to use it for that, but our current method does not handle rough walls. Could be something to look into.
Okay, thanks.
One question from online. Speak up.
I have a question.
Yes.
Can you hear me?
Yes.
Yes.
Yeah. Hey, Louis, nice work. I had a couple of questions on how the genetic algorithm was combining these modes. And
Sure.
so have you tried to go back and see? So I imagine there is some combination of forcing color plus how modes are weighted in frequency that would be equivalent to what? To how the genetic algorithm is combining these. So have you tried going back and looking at that and see if it's doing anything that's like physical? And a second sort of related question was, so all of this is 1D, right? When you do the resolvent analysis.
Correct.
So it wouldn't be very expensive to compute all the modes for all kx, kz, omega, and give all of that to the genetic algorithm. So why are you doing like a sampling in the first stage and then giving it like a limited number of modes to pick from?
Right. So at least with the genetic algorithm that I'm using right now in MATLAB, I can't actually handle more than a few thousand modes before it starts to slow down considerably.
Okay.
So just to limit the wave number space that we're searching, I only restrict it to a combination of modes that have, that low rank sort of characteristic. If I had a better algorithm, genetic algorithm, perhaps I wouldn't need to filter so much. But I think you mentioned something about the forcing color on the genetic algorithm. That's what the Eddy Viscosity model is supposed to do. It's supposed to sort of assume that the forcing has this sort of color and this shape, and that will affect the resulting resolvent modes. So I'm not sure if that answers your question or not. But.
Yeah, I think the model would get a part of the forcing color, but like I think there would be some combination of forcing statistics plus frequency weighting that should give you exactly what the genetic algorithm is doing. And I was just interested in.
Okay. Yeah.
Yeah.
Something to. Yeah. Thank you.
Thanks.
sampling of the resolvent modes, you're only choosing wave speeds that are higher than 10 and plus.
Right.
Why not choose a few to do that?
I restricted it only to like once you start having streaks in that buffer layer, so at around y plus 15, you'll see that that's sort of where these intersect. I guess you could, in theory, select modes lower than that, but we see that we get that skin friction to develop pretty quickly. So the modes that we're using already sort of resemble those near wall streaks pretty well. But I think you could try to lower the wave speed.
It might develop faster.
Yeah. There are certainly structures that exist lower than that. So.
And how many modes do you pick typically?
Yeah.
And
So.
what is the cost of resolvent?
Sure. Examples of cases that we run, and all the cases that I'm using use a similar sort of number of modes. So maybe like 10 to 25 wave speeds in the boundary layer. And then we pick about 20 to 70 modes at each of those wave speeds. So just multiply that to get the total number of modes. And the cost, the 1D resolvent is very cheap to calculate. The cost really is in trying to find an optimization that fits those second order statistics. So you could compute, tens of thousands of modes. That's really not an issue. It's just that now you have to search through all those to find a good solution. So
Genetic algorithm is a pre-processing step, right?
it's a post-processing step. So we compute the modes first. Then once we have all those modes, then we throw them into the algorithm and see what it spits out. Good question.
Next one. I had a couple of questions. First was on slide 30. I know like the DNS, I think Duan's group had like the all the acoustic wave angles, right? How does your compare? I think he has it there, right? Like I think it's the 12, 18, and 22
Yeah,
degrees.
I think we're getting that because the wave angle sort of increases when you go into the core flow, right? So I think we're getting a similar comparison inside the boundary layer, or close to the boundary layer. When we go into the core flow, it's hard to say. It looks like our wavefront angles aren't as steep as what they're getting.
Yeah, but it's also coarser, right?
Right. Our grid is about 3 times coarser than DNS they're running, significantly coarser. So, and as I showed in these plots, something is not matching in terms of the wavelength sort of energy. So.
Prahlad may add to this, like the key thing with all of these recycling or inflow methods is they all work for like when you have a clean flat plate geometry and you have enough developing length. But say if you had like an adverse pressure gradient occurring very quickly, then depending on what development length your profiles start not quite responding to what you need, and you may not have enough region to play with. Have you had any experience with the resolvent approach?
Not that I've noticed so far. I mean, we can see. I didn't really include contours of the development for this case, but we did try a random forcing. So this is it just sort of matches the spectrum, and then it puts in random Fourier modes to match that. And our resolvent forcing is sort of initializing turbulence a little bit quicker than that. Yeah, I'm not really sure how you would implement like a recycling rescaling in this sort of case, since
how does for a bump, like what's up and down, bump, I think. Yeah. Ali did like something like that, using.
Yeah, so I mean, you can do recycle rescaling, but it's not perfect. I mean, if you have an estimate of what the boundary layer thickness is and what the skin friction and response conditions are, I mean, you can map those things.
I actually think there was a cone DNS or LES paper recently that they did like a volumetric rescaling method, and so they were able to do that. So there might be ways now to.
Because you feel that's where like where we have the data, the skin friction and portion doesn't match. Eventually it matches.
Right.
So the recycle rescaling kind of matches from the other ones.
I do have contours of the skin friction or U-tau for the nozzle. I did not include them. I forgot to, but I'll need to check that out again to see where exactly we're getting the skin friction recovery. Yeah.
Again, recycle. So some people fix the mean flow with just recycle. comment on slide 30, compare it to filtered DNS. LES, filtered DNS on your case.
Right, to see, like, are we actually just filtering, or are we changing the structures when we do the LES? Yeah. Because ideally, we would only be filtering out the.
Because you can never get the high frequency.
Yeah.
Real hard question. How would you go to a complicated configuration? What would be the cost penalty going from 1D resolvent to 2D resolvent and arbitrary geometry?
I think it's really not high in terms of computing 2D resolvent modes. There is a MATLAB library for doing 2D resolvent. It's called LinStab 2D.
What about like the topology of the domain? You've got maybe a square, maybe an axis doesn't work, a rectangle doesn't work.
Mm-hmm.
You got to do some kind of curvilinear coordinate space to write the resolvent equations in.
I think at that point it's just a matter of like how you're discretizing it. You just need to. I think you do finite volume, and you could do curvilinear coordinates pretty easily that way. People have done curvilinear 2D resolvent with higher finite differences and other methods, so it is possible for sure.
I think you can do arbitrary unstructured close range to handle. My understanding, completely the resolvent is not once you use the wave numbers and sample get nodes before your simulation. And this double on the once we have the Jacobian for any discretization, 2D, once you have the Jacobian, getting the resolver modes there's been like spurious, sparse, there's been many different methods to compute quickly that in the first mode, because what you need, the first living mode.
Yes.
Quickly, the first resolver mode, there are many new methods to compute that, like Samtide has been doing a lot of work on that, and now they can get even for 3D flows, geometries with 3D wings, they get the resolver modes quickly with this type of, I don't remember the exact name, but for 2D, this would be quick too.
Yeah, it's definitely doable in 2D MATLAB.
If you have a very complex geometry, then you need to do some kind of a finite volume or something. If you have something that you can do a finite difference with curvilinear transformation, then much easier. You can use kind of finite difference with transformation. But those things, I think, nowadays you can do easily.
I think it's doable.
I had one other question.
Yeah.
Like you mentioned for the hypersonic tunnel simulations, the eddy viscosity thing you didn't use, right? I didn't catch that part as to why that didn't.
Yeah,
that
so
it didn't matter. Is it because of the very thin boundary layer there?
I'm not entirely sure, but the branch model that we're using was excessively producing eddy viscosity, and it was introducing TKE like in the outer layer of the boundary layer. Yeah.
It's like making like a little fake wave region above the boundary layer, which is fine. There was this fake region of really high eddy viscosity that we tried to like put a little transition model in it and try to do something to get rid of this guy, but we couldn't. And when you try, even with the real random forcing, it also screwed that up too. It screwed both of them up, having that excessively high TK sitting in the middle of a really more or less uniform flow.
Yeah.
It's probably some random problem that we just.
So that's why I was wondering whether it's also because now it's like almost like a diversity. And also, yeah, and behavior there and
Something like that.
Could be.
Certainly when it's correlated with the Rand's model's behavior, we just didn't get this great program.
Yeah. No, and
shut it off.
and the RANS model, in this case, is it like some SA variant for hypersonic?
No, this was Mentor SST VSL. I think we tried Mentor VSL, both of them with some transition trick thing. But it's interesting.
Yeah. Because I mean that's my question, because anyway you're imposing it on the beam flow, and then for some of these the beam flow is the problem.
It settles out, but it settles out
Farther downstream.
If you had tried to force like a,
Maybe it's further downstream.
absolutely. If you had tried to force simulate 1 or 1.5,
Yeah.
it would have been fine. It was just some garbage near the behavior that we couldn't find. Really, we were trying to match more or less where we had fine voiced his. I don't know what model he used, but he seemed to have no problem with the recycling business cleaning it all up. Actually,
I think it was from. He might have used it from Fluent. I think. I'd have to check. I think it was
Fluent?
I think it was Fluent.
Yeah, he's best to use
Or we
Fluent
could
now.
try to run Volcom with different models to see what we get.
You still got to get TKE for the same.
So the flat plate comparisons, do you use RANS data or DNS data?
Just from the RAND solution. So all of the inflow is built purely from RAND's data. There's no.
Will match the DNS.
Let's go back. Yep. We're, at least for the Mach plate, we're sitting right on top of it. So pretty happy with that result. I didn't declare a variable that should have been complex as complex. So just ignored the complex, the imaginary value, and that really screws up the modes. It did trigger a transition, but not as well as it should have been. It's much better now.
Okay. So let's thank the speaker again.